Now that we've talked about incidence and prevalence and their differences, we now want to talk about comparing measures of incidence and prevalence. That's because any single measure, such as incidence, an incidence measure or prevalence measure, doesn't mean a lot on its own. You really have to compare it with another measure, say some sort of baseline measure, in order to determine whether or not the measure that we're interested in is high or low or just what we'd expect. So in this series of 4 talks, we're going to start by talking about relative risk measures, which we use a lot, and then we'll talk about difference measures, and we'll talk about attributable proportion measures. And at the end of my talk on relative risk measures, we'll talk about standardization of rates so that we can validly compare rates between one group and another. So we often use the term measures of association, and these are summary measures that intended to summarize the magnitude, the size of the relationship between the exposure that we're interested in and the disease outcome. And usually this operates by comparing at least 2 measures of disease frequency, either incidence or prevalence. And usually we have an exposed group and an unexposed group, at least. We may have groups with different levels of exposure, but we're going to start by talking mainly about comparing an exposed group with an unexposed group, because that's the simplest situation, and it works best for teaching purposes initially. So, and we often, we're going to introduce a lot of terminology in this course, and you sometimes hear the term point estimates. So point estimates are often relative risk measures, but they can be measures of risk difference or proportionate measures. But these will make most sense when we come eventually to talk about confidence intervals. And you'll see that the point estimate is always sort of in the middle somewhere of a confidence interval. But we'll leave that till a future talk. So we use 3 types of measure for comparing disease frequency. So there's the ratio, and usually in epidemiology it's a measure in an exposed group compared to a measure in an unexposed group. Then there's a difference. We take the difference between those 2 measures. We're going to be discussing that. And then there's a proportion, and usually we use proportion in the sense of the proportion of the health outcome that we're interested in, which is potentially accounted for by the exposure that we're particularly interested in at the time. So let me now introduce the 2x2 table. We use 2x2 tables a lot in epidemiology, and I and others keep them in our heads just so that we can kind of do quick mental calculations, and you'll probably get used to this, trying to work out relationships between disease and exposure. So this is the 2x2 table, sometimes known as a 4-fold table, is the simplest example of a class of tables, sometimes referred to as contingency tables. So they can be n by m tables, and n and m are 2 integers, but we're not going to worry about that at this stage. We're just going to be talking about 2x2 tables. So here we have a typical example. So we have exposure. And we're going to classify people as either exposed or not exposed. And then we have disease. We're going to classify people as having the disease or not the disease. And so, of course, everybody falls into one category of having disease or not, and having exposure or not. And then if you count the numbers of people in those 4 categories, then the counts are A, B, C, and D. And so everybody falls into one of these 4 boxes. And then we have the column totals, and we have the row totals. And so this form of contingency table is commonly used for cumulative incidence and prevalence, which I've already talked about. So, and A, B, C, and D are simply the numbers of people in the study. So we're going to be using 2x2 tables all the way through, but we're going to start by talking about ratio measures. So ratio measures compare a measure of disease frequency in an exposed group, and we compare that same measure to the corresponding measure in the unexposed group. And we use the term relative risk. And it's often used very loosely and generically, whereas we might be really comparing two measures of, say, incidence rate, when incidence rate ratio would be a more appropriate term, or we might be comparing measures of prevalence, where prevalence ratio might be a more appropriate term, but people or epidemiologists commonly use this term relative risk, and you usually have to look a bit further than that to find out what sort of relative risk measure they're actually talking about. Could be an incidence rate ratio or a prevalence ratio. Now, because we're commonly using a sample in our studies, we usually refer to the measure which we get from our studies as a relative risk estimate. So sometimes people leave the word estimate off, but strictly speaking, because we're using a sample of the overall population to estimate the relationship between, say, smoking and lung cancer, and because we're not using the whole population, we're using a sample which is estimating the population parameter. So we commonly use the term relative risk estimate, although estimate sometimes gets left out. Now, our relative risk estimates usually very simple conceptually. They involve the division of the risk in the exposed group by the risk in the unexposed group, and we can use that simple measure just to illustrate the prevalence ratio. So the prevalence ratio for P, and I'm just using the generic term here, relative risk. So it's the prevalence in the exposed group divided by the prevalence in the unexposed group. So if you refer back to the 2x2 table, you'll be able to see exactly how this is calculated. A divided by A plus B, and then that is all divided by C plus D. And it's exactly the same for the cumulative incidence. Cumulative incidence in the exposed group divided by the cumulative incidence in the unexposed group. So this might be perhaps more accurately referred to as the cumulative incidence ratio, and this might be more accurately referred to as the prevalence ratio. But as I say, we often use the term relative risk in a generic sense. So basically, the relative risk gives information on the relative effect in the exposed group relative to the effect of no exposure on the risk of disease. So, and you can think of it as how many times higher or lower in the exposed group the risk is compared to the unexposed group. And we say that this is commonly used in etiologic research. So etiologic research is research which is attempting to find causal relationships between an exposure and a health outcome. That's etiologic research. So the interpretation of the relative risk is fairly straightforward. So if we have a relative risk of 1, in other words, the risk in the exposed group is the same as the risk in the unexposed group, you're dividing the same number by the same number, and so you get 1, naturally. Now if the relative risk is 2, there's a doubling of risk in the exposed group compared to the unexposed group. So that's, I think, very straightforward. If we had a relative risk of 1.6, we might say that there's a 60% increased risk of disease in the exposed group compared to the unexposed group. And of course, it's not always, the relative risk is not always greater than 1. It may be less than 1. So if we had, for example, a relative risk of 0.5, we'd say that the exposed group has a half the risk of the unexposed group. In other words, the exposure appears to be protective. And that might be, for example, if somebody is taking some vitamins, say, and if the vitamins had some protective effect against the risk, then it would be you would end up with a relative risk of less than 1. Now, I just want to briefly talk about this term association, which we often use. And association is fairly loosely used to indicate that there is some evidence of a connection between the exposure that we're interested in and the disease or health outcome. And sometimes you might get people might use the phrase a statistically significant association. And we'll talk about what statistical significance means and how useful it is. But the fact that we have an association between an exposure and a disease doesn't necessarily mean that there's a statistical relationship or a strong statistical relationship. It just means that the relative risk is somehow different to 1, and it suggests that there may be some relationship between the exposure and the disease, but it is used in a fairly loose way in the epidemiology literature. Now, just the fact that we have a high or a low, below 1 relative risk, doesn't in itself mean that there really is a relationship between the exposure and the disease, because high or low relative risk estimates can be produced by biases and also by chance. So we're going to discuss these issues in future talks, but for the moment we can think in terms of there being at least some evidence of an association when we have a relative risk that departs from 1. It's either higher or lower, particularly if it's markedly higher or markedly lower. So let's have some examples. So I'm going to use this example, and I've modified this somewhat from an example that occurs in your book. So in this instance, we're going to be talking about comparison of a polluted city and an unpolluted city, and so the question, of course, is what is the difference that the pollution makes? So we compare these two cities, and we're able to count the numbers of deaths occurring in the cities. So these are the data, and it's set out in terms of the 2x2 table, so you can see the numbers of deaths that occur in the unpolluted city and in the polluted city, and the numbers of people who don't die, and then the totals, of course, the row totals, and of course the column totals over here. Total number of people in the study is nearly 3,000. Okay, so those are the data. In the data analysis, so in this instance we'd calculate a relative risk estimate, which is really a cumulative incidence ratio. So it's the cumulative incidence in the polluted city divided by the cumulative incidence in the unpolluted city. So the calculation is very straightforward. You can see if you look back at the 2x2 table, we are simply dividing the cumulative incidence in the polluted city, 291 divided by 1,351, by the cumulative incidence in the unpolluted city, 232 divided by 1,631. So that's straightforward, and we end up with a cumulative incidence ratio of 1.51. So we might say that people living in the polluted city are estimated to be about 1.5 times more likely to die than people living in the unpolluted city. So, in other words, we might say that the pollution increases the risk of mortality by 50%, approximately. And so we could set out the data by adding an additional column, set out the calculation by adding an additional column to the 2x2 table, and just to display a relative risk. And so the relative risk in this is a convention, usually in the reference group, or in this case the unpolluted city. The relative risk is by convention 1, and that's because we're basically dividing the cumulative incidence in the unpolluted city by itself, so naturally we get 1. But if we continue to, and we divide the cumulative incidence in the polluted city by the cumulative incidence in the unpolluted city, we get 1.51, as we just showed, so we can set it out in this way. Now, to digress briefly, we often have the situation where we have levels of exposure. So I've just been showing exposed versus unexposed, polluted versus unpolluted, but it may be that we have several levels of exposure, and basically the way it's displayed, the data or the results are displayed, is very much like this. And so this is an example of data regarding electromagnetic field exposures. So these low-frequency electromagnetic fields are really all around us. They're power frequency fields, 60 cycles per second or 60 hertz, and so given off by just basically the electricity system that we use to run our computers and all of our electrical equipment. So it's been a long and controversial issue as to whether or not certain cancers are associated with these low-level electromagnetic field exposures, and it's still really not completely resolved. But here's some data from a study, and these suggest that, well, first of all I should say it shows that the children who have low exposure and children who have medium exposure and high exposure. Now everybody has some exposure, so you can't have an unexposed group. So the low exposed group becomes the reference category, and so of course by definition it has a relative risk of 1. And then we show data for the medium exposed group, children, and we can see the relative risk there is 1.24, and in the high group 1.32. So you can see there's evidence here of what we might call an exposure-response relationship, and we'll talk about those in more detail in a future lecture. But really, exposure-response relationship is just evidence that as exposure increases, as it does here, going from low to high, low, medium, high, then you can see the relative risk increases. Now, when you get that sort of relationship, it adds to the evidence that there may be some causal connection. Doesn't prove it, because there's still issues of bias and chance that might have kind of influenced these results, and we'll talk about those in the future. But it does add to the evidence that maybe something's going on. So now I want to talk about the contingency table for incidence rates. It's a little more complicated than just talking about prevalence or cumulative incidence. So we've added in another column. This time we've added in person time. So now the person time, and this is the person time in the unexposed group, and so this person time is contributed by people who got the disease and who didn't get the disease. And the person time in the exposed group is similarly contributed by people who in the exposed group who got the disease, the C, and those who didn't get the disease. So it's important to understand, but B, the numbers B and D do not directly contribute to the calculation. So the calculation of incidence, of course, is the number of cases in the unexposed group divided by the person time in the total unexposed group, so both A and B. Similarly, in the exposed group, both C and D are contributing to the person time, but only C, the number of cases of the disease in the exposed group, actually contributes to the incidence calculation. So the calculation of the incidence rate ratio is very straightforward. It's just the incidence rate in the exposed group divided by the incidence rate in the unexposed group. And so just referring back to the 2x2 table, you'll be able to see how this is calculated. Okay, so if we go back to our comparison of the two cities, the unpolluted and the polluted city. So this time I've added in person time, but you can't see the numbers who didn't get the who didn't die there, because they don't directly contribute to the calculation, but they are important in terms of contributing person time. So those are the data, the same number of deaths, and then if we do the data analysis, we calculate the incidence rate in the polluted city, divide by the incidence rate in the unpolluted city. We simply use those data in the previous table, and we calculate an incidence rate ratio of 1.7, in which case we might say that the people living in the polluted city are about 1.7 times as likely to die as people living in the unexposed city. Now this is greater than the corresponding measure using cumulative incidence, and it will usually be the case that the two measures are a bit different, maybe not greatly different, but generally speaking the incidence rate is the most accurate and the most valid, but we would calculate that if we had the data, but we often don't have sufficient data to give us a measure of incidence rate or incidence rate ratio. So we would often just use the cumulative incidence ratio. Now this is how we set out the data, very much the same as when we looked at cumulative incidence ratio. Again, the reference category is 1, and then we show the relative risk here in the table. Just to reiterate, we use this term relative risk very generically, and but it's often better to use the more precise measures, such as incidence rate ratio. And relative risk, or risk ratio, is another way of putting that. It's strictly speaking a cumulative incidence ratio, sorry. And because if you remember, cumulative incidence is often referred to as risk. So a risk ratio, or relative risk, is strictly speaking a cumulative incidence ratio, but we use the term relative risk very loosely, which is a pity, but epidemiologists seem to do it very frequently and generally. So if we can have the data, if we can get the data to measure it, the incidence rate ratio is the best one to have. It's the most meaningful and most valid. And really, most other studies, when we calculate a cumulative incidence ratio or a prevalence ratio or an odds ratio, but we'll be talking about odds ratios when we get to case control studies, because they're particularly relevant to case control studies. But all of them really, if they're not exactly an incidence rate ratio, they're all trying to estimate what the incidence rate ratio would be if we're able to carry out a study to obtain that sort of measure, which we often can't do. So generally speaking, I would encourage you to use the more precise measure, such as prevalence ratio, incidence rate ratio, and so on. Okay, another ratio is that we sometimes use is the proportionate mortality ratio. So this is mainly used when we only have mortality data. So we may have mortality data, say, in two populations, but we don't have anything on the general population. And so when we calculate a proportionate mortality ratio, we are comparing the proportion of deaths attributed to a specific cause of death in one population to the proportion of deaths caused by that same specific cause of death in the other population. Usually the other population would be our reference population, or which might be, say, an unexposed group. And this would be, in both cases, relative to some sort of specific time period that the deaths would occur. So the calculation of the PMR is pretty straightforward. So it's the number of deaths from disease Z in the exposed group divided by all deaths in the exposed group. And then that's divided by the number of deaths from the same disease Z in the unexposed group, divided by, and that in itself divided by all deaths in the unexposed group. So, and then having calculated that measure and that measure, you just divide one by the other, as we have done with all the other ratio measures, and we get the proportionate mortality ratio, which gives some estimate of the the proportion of deaths in the it gives a measure of an estimate, shall we say, of what the incidence rate ratio might be if we're able to carry out a study to get the incidence rate ratio. But in this case, all we have is deaths, just a mortality database. So we can extend this approach to incidence, and usually it's limited to cancer, and we would calculate a proportionate incidence ratio. And the approach is very much the same. Usually we're limited to cancer just because we often have data from cancer registries for different sorts of cancer as a kind of a class of disease. So the method is exactly the same. If we can identify an exposed group and an unexposed group, we calculate the proportion of new cases of cancer Y, whatever cancer Y may be, in the unexposed group, and divide it by the same proportion in the, we start with the exposed group and we divide it by the proportion in the unexposed group. So the proportionate incidence ratio is simply the proportion of cancer cases in the exposed group divided by the same proportion in the unexposed group. And here's an example using data from the California Cancer Registry, and I've long had an interest in cancer in firefighters, and these are some actual data that I obtained from the California Cancer Registry. So looking in this case at whether malignant melanoma is more common, is a higher proportion in firefighters than in other occupations, because the Cancer Registry has a data field for occupation. So I calculated the proportion of cancers in male firefighters that were melanomas. So there were 323 melanomas, and recorded during this time period, 88 to 2003. In the Cancer Registry, there were 3,659 cancers in male firefighters. So, and then I took all the other male occupations, and there were nearly 42,000 melanomas in all the other occupations, and a total number of cancers of 800,000. So it's simply dividing this proportion here by this proportion here, and you come up with a proportionate incidence ratio for melanoma in California firefighters of nearly 1.7. So that is suggestive of an association between firefighting as an occupation and malignant melanoma. So it's an example of how you could use the proportionate incidence ratio. So PMRs and PIRs are often relatively easy to calculate, particularly if we can get data from a mortality database or a cancer registry. But they have a big limitation, and that's that well, there are two limitations really. They don't really represent the true person time experience of the underlying population. And if we were really going to calculate a proper, if we're trying to estimate an incidence rate ratio, then really we want to try and estimate the person time distribution in the underlying population. But people who get cancer and people who die are on average less healthy than the general population, so they don't really estimate it extremely well. And the other thing is that when one cause of death or one cause of cancer changes, then because we're talking about proportions, the proportions of the other causes of death or types of cancer will correspondingly adjust. So they're not independent because the proportions really ultimately have to sum to one. So those are limitations of the PMR and the PIR. They can be very useful if all we have is a database on health outcomes. We don't have any real population data. but they're not as good as measures based on the general population that we're looking at.